Hello all, we will continue with the questions of the second online assessment. Okay, coming to next question. A finite set of vectors that contain the zero vector is. A finite set of vectors that contain the zero vector is linearly independent, linearly dependent, both may be possible, cannot say. Finite set of vectors that contains a zero vector. If it contains a zero vector means, what does that mean? Zero vector means scalar multiplied. If 0 is the scalar quantity, if that is multiplied to some column vector or any other vector, then it will result in a zero vector. Right? Means one of the vector is a linear, one of the vector is a combination of the other unique vectors in the vector space. Okay, that is the meaning. So what is a linear dependent means? So it is a linear dependent. It is linearly dependent on the other vector in the vector space. Okay, so solution is this. Let me define it clearly. Linearly dependent means if at least one of the vectors, if at least one of the vectors in the set can be defined as a linear combination of other. Okay, so zero vector means it's a linear combination of some other vector, right? It's a zero multiplier of some other column vector or row vector, right? So it is a linear dependent, it is not independent. So any vector which contains zero vector is linearly dependent vectors. Okay, coming to 11th question. If W is a subspace of finite dimensional vector space, finite dimensional vector space means Rn is finite, some value 1 2 3 4 5 6, okay, countable value, vector space V, then W is a finite dimensional. Obviously, see, subspace is nothing but as it acts like a subset of a set. So if we consider vector space as a set, then subspace is nothing but as a subset, right? So W is also finite. When this is finite, then anything residing the finite boundary is also finite, right? So A is true, W is a finite dimensional, right? B is dimension of W is less than or equal to dimension of V. Obviously, it can be maximum, it can be equal to, because it's a subspace, it may have the same number of vectors as vector space V has. So that is the maximum limit. So it can be 0, it can be equal to, or it can be less than. See, subspace can be, this is one kind of, this is V and this is W. Okay, the one more thing is we can draw like this also, right? Sorry, see, somewhere it touches. If touches means, so dimension of W might be equal to dimension of the vector space. So it can be equal to or it can be less than. It can never be greater than. So B is also true. Coming to C, W is equal to V if and only if dimension of W is equal to exactly the same situation what I explained here in set theory. See, if the same two circles are of the same radius, then V and W will be same. This can only happen when dimension of W and V are the same. Dimension of W and dimension of V means the same number of vectors are incorporated in the vector space. Okay, so this is also true. So solution for 11 is all of the above. Does elementary row operations change the null space of a matrix? No. See, elementary row operation, what you do, you take a pivot element and you try to make 0 under the pivot elements equal to 0 under that pivot element. Okay, so null space is the one which is a free variable. If you remember, if you try to solve the matrix, if you try to do row operation, perform row operation to get the upper triangular matrix or lower triangular matrix, what you used to get? These are the pivot columns and one was the free variable. So free variable was a null space. Okay, so after doing the row operation, null space will never change. If one null space exists, if one vector exists in a null space, then that vector is also a will always be there even after elementary row operation. So does elementary row operations change the null space of the matrix? No. Does elementary row operations change the column space of the matrix? Yes, obviously, right? To find out the column space, dimension of column space, what we do? We do the row operations and we'll try to find out whether the third column is a linear combination of the 1 or 2. We always try to find out whether any row or column is a addition of some other columns, or we try to check the uniqueness of the column and rows, right? So that is the elementary row operation change the column space. So finally we will arrive at the main dimension of the column space, which will say that only some columns are unique. So obviously it is yes. Does elementary row operations change the column space of the matrix? Yes. We try to change the column space of the matrix. Okay. 14th question. If A is any matrix, then dash space of A have the same dimension. When we were studying 4 fundamental subspaces, what are the 4 fundamental subspaces? One is column space, then null space, then row space, and left null space, right? Do you remember when we tried to find out the dimension basis for column space? On similar lines we found out for the row. How we did that? We took the transpose of the column space, right? We took the transpose of the column space. So row and column space will have the same dimensions. Okay. So if A is any matrix, then row and column space of A must have the same dimension. C is the answer. Coming to 15th question. An orthogonal set of non-zero vectors is an orthogonal set of non-zero vectors. See, non-zero vectors means, orthogonal means what? Perpendicular, right? When they are perpendicular means they are never dependent, right? They are different. How can I say this is? See, a value on one vector doesn't depend on the value on the second vector, since they are orthogonal. Orthogonal means perpendicular, means the dot product of the two vectors is 0. So answer is linearly independent. Orthogonal set of non-zero vectors are always linearly independent. Okay. See, linearly dependent means you can define like this also. If linearly dependent means it is somewhere scalar multiplication of the some other vector, right? If there are two vectors which are orthogonal, how can it be a scalar multiplier of the other vector? If that is so, then both the directions of the vectors will be on the same line space, right? So there it will never be perpendicular. So which is not orthogonal, right? So it is not possible to have a linear dependent vectors as an orthogonal set. Okay, orthogonal set will always have a linearly independent vectors. Okay, thank you.